So today we are going to start ATP, alternative to practical. And let me tell you, this is the easiest paper. Okay, why I have choose to do a 2023? We are going to do the previous ones as well. But the thing is that from 2023 onwards, you are going to have a 40 marks paper. Earlier, the paper was 60 marks. So we are going to do that as well. So you got the idea, but now it's of 40 marks and there is a very simple format. There are very specific questions which are always repeated. So you have, if you will practice them in the similar manner, you are going to, uh, easily get the mark in this. Okay. So let's start with the first one. Okay. Yeah. Question number 1. A student investigates the rusting of iron. Figure 1.1 shows the apparatus the student uses. Okay. Apparatus X, and in part A, they are asking you to write the name of the apparatus X, name apparatus X. So see, okay. So what will be your answer? What is apparatus X? I hope everyone knows. Okay, good answer. It's a test tube. Okay. Remember, sometime you will find instead of test tube, they have written a boiling tube as well. So the difference between the test tube and the boiling tube is only that boiling tube has a bigger diameter as compared to the test tube, and it is usually used when we have to heat some substance. So for heating of a substance, we usually use boiling tube as well. So either can be considered. Now, in the next part, state why a stopper is used in experiment B. Okay, so see the objective first. What the student is investigating? It is investigating the rusting of iron, right? So it is investigating the rusting of a iron. So in experiment A, there is no stopper over here. In experiment B, there is a dry air, iron nail, and a stopper. So it means we or the student want to prevent any water from here. No, Vara, not oxygen, because see, it's a dry air. It's a air, then it contains oxygen, right? Because it's an air over there. And remember, if you guys remember, for the rusting, there are two conditions. If both were there, then rusting would occur, and both the conditions are oxygen and water both. Okay. Yes, Amal, very good. Yes, Josefa, very good. Yeah, so Ahmad Mushtaba, very good. No, Rahim, your answer is wrong. See, what to prevent water vapors or to prevent entry of a water, because see here air is there, and if it's air, then it means oxygen is there. I just told that the test tube and the boiling tube both are same thing. The only difference is that the boiling tube has a bigger diameter. So either you write boiling test tube or boiling tube, both are considered as correct. Okay. So why we put a stopper over here? There is a air inside, which means oxygen is there. So we prevent water from entering the test tube. Okay. So here what you will write? To prevent water from or to prevent water entry inside test tube. Is this clear to all of you? Okay. Now, state why the water in experiment C is boiled before use. Very good, Umar. Just give me a minute, please, everyone. Yes, to remove oxygen. Very good. So, to remove, basically, you can write to remove oxygen which is dissolved in water. Is this clear to all of you? Now, state why a layer of oil is used in experiment C. Yes, very good, Amal. Yeah, to prevent entry of O2, very good. Yes, I have seen. Yes, Zed, you are asking, see how is the oxygen getting removed? Basically, if you see, there is a in water, oxygen gases are dissolved. That's why the fishes and the aquatic life survive under the water because of oxygen. O2 is being dissolved. So when we boil it, H2O stays the same. If there is some gas, some oxygen gas, O2 molecules are there, they escaped away. So that's how it is removed. Okay. And yes, the layer of oil is there to prevent entry of oxygen. Is this clear to all of you? Now, next part. The experiments are left for 1 week. Predict in which of the experiment the nail will have rusted. Yes. In which experiment? In experiment A. Very good, because experiment A has a opening over here. Water is there and air is also getting inside, which is providing the oxygen. So both the conditions are there. So in experiment A only rusting happens. In experiment B and experiment C, there would be no rusting. Okay. So in experiment A, nail will rust. Now, explain your prediction. So, yeah, what are the conditions? You have to mention the conditions. Yes, Suzefa, you are right. Both oxygen and water are present or are needed for rusting. Both oxygen and water are present. Yes. Now, question number 2. So see, in every case, paper, you are going to get one question of a titration. The first one usually varies. Sometimes it will from rusting or any instead of rusting, it's from chromatography or fractional distillation or any other experimental technique. All the question number 1 and question number 2 always comes, one question always comes from the titration. Okay. Then one question always comes from the identification of ions. And for that identification of ions and gases, you are provided with these tests at the end of the paper, at the end of the exam paper. Okay. And there is a one question of designing of an experiment, which is of usually 6 or 7 marks, which is over here. So we are going to discuss it. And every time there is a, different, they give you a different scenario, and you have to read the question very carefully, and then you have to design the experiment. So you can say it is always an unseen thing. Okay. Now, yeah, question number 2. Okay. And you guys have to be very focused. No, no, not necessary, Josefa, every time. Okay. Aqueous ammonia is a solution of ammonia gas. And if you recall further, aqueous ammonia is a weak alkali or a weak base. A student titrates 2 samples of aqueous ammonia A and B with 0.5 mole per dm cube hydrochloric acid. So see, it's a concentration, and it's a concentration of hydrochloric acid. The student does 4 titrations, 2 with A and 2 with B. Okay. A student rinses and fills a burette with 0.5 mole per dm cube hydrochloric acid. Okay. Uses a volumetric pipette to add 25 centimeter cube A to a conical flask. So what we are taking in the conical flask, A, and A is a one solution of aqueous ammonia. Add 5 drops of methyl orange indicator to the conical flask. Place the conical flask on the white tile. Why we put it on the white tile? If some time examiner asks you for, or you can write over here, to observe the color change. The color change would be very visible when you observe it behind the white tile. Okay. Okay, now in step 5, 0.5 mole per dm cube hydrochloric acid from the burette while swirling the contents of the flask, adding drop by drop near the end point until the solution just changes the color. Okay. Empties the conical flask and rinses it with still water. Repeat step 2 to 6. Okay. Then repeat step 2 to 7 using aqueous ammonia B instead of aqueous ammonia A. So they have performed the titration of a hydrochloric acid 2 times with ammonia A and then 2 times with ammonia B. Okay. Now, figure 2.1 shows the burette reading for 2 titrations with A. Okay. So that is the initial reading of the burette when none of the acid is being added in the flask, and when the color changes, this much amount of the acid has been added in the flask. So it's the final, and same goes for the titration too. Okay. Record the burette reading in table 2.1. Complete table 2.1. See, it's highly scoring question. Okay, remember, it's the one which is the highly scoring question from the paper. Just give me a minute, please. Okay. Now, final burette reading. If you see the final burette reading over here, the scale is at 15.2, right? And the initial burette reading is, yes, that usually most of the students do mistake over here. It's not 0, it's 0.0. You have to write with that one decimal place. So final burette reading of titration 1 is 15.2 and initial burette reading is 0.0. If remember, if instead of 0.0, you will write just 0, you will not get the mark. Remember this thing, okay? So the volume used is actually calculated by subtracting these two values, final minus initial. So when I did final minus initial, it's 15.2. Okay. Now titration 2. If you see, the final is 30.2 and the initial is 15.2. So 30.2, okay, it's 0.0, remember, and 15.2. So if I subtract it, I will get 15.0. See, if you do this thing, you will again not get the mark. And remember, for each one carries 1 mark. So if in any one row you did a mistake, you lost 1 mark. It's 15.0. Okay. Now, if you see, figure 2.2 shows the burette reading for one of the titration with B. Okay. Record the burette reading for titration 4. Okay, it's a titration 4 in table 2.2. Complete table 2.2 with the volume used in each titration. For titration 3, they have given you the readings. So you have to just subtract them. So what you will get 34.7 over here, right? And now, if you see the final is 35.5 and initial is 0.6, right? So 35.5 and 0.6. If you subtract them, what is the answer? 34.9. Till here, is this clear to all of you? I think these are the easy one. Okay. So see here they have asked, explain why the student uses a white tile in these titration. So to observe the color change accurately or more accurately. Yeah, it would be a more accurate color change would be observed. Okay. Now what they are saying, calculate the mean volume of 0.5 mole per dm cube hydrochloric acid needed to neutralize 25 centimeter cube of A and 25 centimeter cube of B. Remember, in each titration, 25 centimeter cube of B of ammonia is used. So for solution B, you have these two values. That is 34.7 plus 34.9 divided by 2. So you will get the mean of 34.8, right? And here the values are 15.0 and 15.2. Yeah, Yasir, more accurately will be needed or necessary to write. Yes. So it's 15.0 plus 15.2 divided by 2. So you will get 15.1. Yeah. Okay. Now, next part. The equation for the reaction between hydrochloric acid and aqueous ammonia is shown. use the mean volume of acid needed to neutralize 25 centimeter cube of A. Calculate the concentration of ammonia in A. So see, they are asked you to do the asking the concentration of ammonia in A. Which one, Oliver? If you see over here, for in A, for the solution A, these are the volumes of hydrochloric acid. So we take the mean of these two. Mean average. So you will add these two and divide by 2. And for titration with the solution B, we have these two values. So we have to take the mean of these two values. Now is it clear, Oliver? Okay. Now, the mean volume of acid A needed to neutralize 25 centimeter cube of A. So if you see, for A, 15.1 is the volume, right? 15.1 centimeter cube. So volume of acid over here is 15.1 centimeter cube. This is the volume of A. And you have to find the concentration of A. Okay. This is the volume of A. This is the volume of HCl. And we got the concentration of that they have that they provided to us over here. See, 0.500 mole per dm3. So if you recall the scheme, what I have told you, what you need to do, whichever substance quantities are given, turn them into moles. So we have a concentration of HCl and we have a volume of HCl. So I can find the moles of HCl by multiplying the concentration of hydrochloric acid with the volume of hydrochloric acid. And in this concentration, we always use volume in decimeter cube. And here the volume is always given in centimeter cube. Josefa, it's wrong. Volume of acid is 15.1. 25 is the volume of A. So see, you have to be very vigilant which values you are using. So 0.500 times volume, which is 15.1 divided by 1000. Can anyone calculate it and tell me the answer, please? Yes, please, anyone? Okay, it's 0.0. Shamir, your answer is wrong. 0.00755 moles. Is this clear? Now, see, one important thing over here, they have asked you to use appropriate number of significant figures, right? And if you see over here, how many significant figures this value has? 3. And how many significant figures this value has? 3. Right? So that's why you have to keep the 3 significant figures over here. So either you can write 7.55 exponent minus 3, or either you can write in this way. Both are considered as correct. But if you round it off, as I have seen some students answer me like 0.0076 or 0.007, so you will not get the mark. Okay, so we got the mole, and these are the moles of HCl. So what I have told you to do the next step, you have to take the ratio of the substance whose quantity is given to the ratio of the substance whose quantity is asked. So I will take the ratio between hydrochloric acid and ammonia. And if we see the ratio is same, so it means I am going to get the same moles for ammonia aqueous ammonia. So it will be 0.00755 moles of ammonia. So we got the moles of ammonia. Now we have to find the concentration of ammonia. So the concentration of ammonia would be moles of ammonia divided by volume of ammonia. So the moles of ammonia would be 0.00755 and the volume is 25. But remember that we have to use in decimeter cube, so 25 divided by 1000. Now can anyone solve it and tell me the answer, please? Let me check one thing. 0.00755. Okay, let me check one thing. Okay, so it's 0.302 mole per dm cube. Is this clear to all of you? Now, next part. Calculate the volume of ammonia gas measured at room temperature and pressure RTP dissolved in 25 centimeter cube of A. Okay. So we know at RTP how many volume is occupied by 1 mole that they have given you over here. That 1 mole of any gas occupies 24 decimeter cube. That's they have told you. Okay, what does this mean? 0. Mole per dm cube. What does this mean? Isn't it this means that moles in 1000 centimeter cube? That's what mole per dm cube, isn't it? Is this understandable to all of you? Okay, so it means I can make the ratio over here that 0.302 moles are present in 1000 centimeter cube. So if there is a 25 centimeter cube, then it must have a X number of moles. Yes, what is your query, Khatija? Yes, Khatija. What does see 1 dm cube means 1000 centimeter cube, isn't it? So it's a mole per dm cube. So it means these are the number of moles which are present in a 1 dm cube, or you can say these are the number of moles which are present in 1000 centimeter cube. Is it clear? Okay. So that's how I make the ratio, because they have asked you to find the moles of ammonia which is dissolved in 25 centimeter cube. So if I calculate the X, so X would be equals to 0.302 times 25 divided by 1000. Can anyone tell me the moles? Yes, can anyone tell me the number of moles? Okay. So we got 0.00755. These are the moles of ammonia which are dissolved. So what will be the volume? As they have given you this information, 1 mole is occupying 24 decimeter cube, right? So 1 mole occupies 24 decimeter cube. So if there are 0.00755 mole, then they would occupy X decimeter cube. Yes. So calculate the value of X. X is 0.181. So we will write 0.181 dm cube. Is this clear? Now, next part. Use your answer to D and F to calculate the volume of ammonia gas measured at RTP to dissolve in 25 centimeter cube of B. Okay. So see, this is very important, and this is the one which is the trickiest part. Yes, Yasir, do you want to ask something? Yes, what is the problem in part F, Yasir? See, the second ratio, we made it from here. See over here, 1 mole of any gas occupies 24 dm cube at RTP, right? So you can do the other thing as well. You know the moles, you make the formula for the volume. That volume of a gas is equals to moles times 24. Why 24? Because they have asked you the volume in decimeter cube. So we have to multiply the moles by 24 decimeter cube. So moles are 0.00755 multiplied by 24. So you will get the same answer. Is it clear now? Okay. So what they are asking, you have to take the help from part D and part F. To find, and you have to calculate the volume of ammonia gas measured at RTP, which is dissolved in 25 centimeter cube. So if you see in D what we get, let's see. Okay. In D part, we have the volume of acid which is used to neutralize solution A and solution B, right? And in F part, we got the volume of ammonia. Okay. So see over here, volume of HCl for A, is it 15.1 centimeter cube that we took the ratio? Hania, I think your internet connection is not well, that's why. Otherwise, you can just leave the class and join back. And the volume of HCl for B was 34.8. Is this clear? Is my screen is still lagging? Yes, how many of you are facing that my screen is lagging? Okay. Now, if you see by which factor they differ from each other, if I divide these two, I get the factor that how much more HCl is being used for B? Can anyone divide it and tell me the answer? 34.8 divided by 15.1. It's 2.30. So it means that let me write it over here, that this volume times 2.30 makes this one. So it means that the same approx, 2.30 times ammonia would be greater in solution B. So if the volume of ammonia in 25 centimeter cube of solution A is 0.181, then the volume of ammonia in 25 centimeter cube of solution B would be 0.181 times 2.30. Can anyone do it and tell me the answer? Zero 0.181. Yes, Hadi. See, if you recall from the start, we have two different solutions of ammonia. One is solution A and one is solution B, right? Okay, now everyone listen it carefully. For solution A of ammonia, we use this much volume of acid, right? And for solution B of ammonia, we need this much volume of acid, right? So what it indicates that this solution, this is the volume of HCl that is used, but this indicates that B has a more ammonia, isn't it? Because more HCl has been used. Yes, is this understandable to all of you? Now the question arises, how much more ammonia is there? So what we did, we took the ratio of both the volumes of HCl. So we got that this much ammonia, this much HCl is more used. So it means almost that much amount of ammonia is more in B. Is this understandable now? Yes, Khatija, did you understand this as well? So that's why we did it with 2.30. We multiplied 2.30 with 0.181. Now, okay. So the answer is 0.418. Okay, now tell me, because this is the volume of ammonia in solution A, right? So obviously, if this much more, this much times HCl equals is used, so the volume of ammonia would also be times with the same factor to get the volume of ammonia in solution B. That's why we multiplied the volume of ammonia, that is the volume of ammonia in solution A, Yasir. And we have to multiply it with the factor. Yes, most of the time it's usually the same. Now, next part. The student rinses the burette with 0.5 mole per dm cube hydrochloric acid. Okay, it's a concentration. Immediately before it is filled. Explain why the student should not rinse the burette with distilled water immediately before it is filled with 0.5 mole per dm cube hydrochloric acid. So we are going to use the burette to record the volume of hydrochloric acid, isn't it? So if we rinse it with the water, so some of the water would be left behind. And if some of the water would be left behind, then we add the HCl. So the HCl would get diluted. If you just write inaccurate volume, you are not going to get the bar, Josefa, because that is a very vague answer. Okay. So keep your answers specific. So some of the water left, hence HCl gets diluted. Is it clear to all of you? Okay. Now, suggest why universal indicator is not suitable for use in these titration. Yes, so I wrote 2 points. One first point is, see, some of the water is left. Diluted means there is a water. So when we add the ammonia, oh sorry, HCl in it, there is a water inside. So that instead of the exact amount, the lesser amount of HCl would be entered, and there is a water which makes it makes it dilute. Diluted means that there is a water. So obviously, due to the water, not the actual quantity of HCl gets filled inside the burette because of some water present inside. Is it clear, Rahim? Okay. Now, yes, it is not suitable because they change a variety of colors, so there would be no clear endpoint. So it does not show clear endpoint. Yes, Josefa, what you didn't understand? See, universal indicator usually changes the color at different pHs, right? It's not like that. Just in acidic, the solution, it has a specific color, and in base, it has a specific color. During the range of acidic being strong to till weak, the color is changing continuous gradually. And then when it turns neutral, it again changes the color. So there is a continuous color change, and there are so many colors. So that's why there would be no clear color change over there on endpoint. I hope till here it's clear to all of you. Okay. The thing is that if we wash it with the water, so all of the water must not be removed. Yes, we can use thymolphthalein, we can use phenolphthalein, we can use bromophenol, we can use a litmus indicator. So yes, Moise, when we wash it or with the distilled water, so all of the water must not be removed. So there must be some water in there, right? So when we add it HCl, that HCl gets mixed with the HCl. That HCl gets mixed with the water, which make it diluted. Is it clear to all of you? Okay. So we are keeping the class till here. And tomorrow, same time, we will be continuing and we will be doing the rest of the paper. Okay. So see you everyone in the next class. Take care. Allah Hafiz.